So I'm Pablo Perez. I work for Nokia. I've been working in video quality for and other stuff as well as video quality for almost 20 years. So I would like to talk a bit about how we could think about video quality and a bit of some of the things that I've learned from these years till now. Okay, so how like normal humans think about video quality. So if you ask people, normally people will say, okay, this is like 4K, this is HD. When I started working in digital television, HD ready was the way that, if you remember, people were trying to reach HD quality before reaching it and so on. But we video quality people are normally really not normal human beings. So I will try to give you an idea of how this works, and it's about a story that happens to me, basically discussing video quality and so on over video streams on the digital television at that time, and then an ad came to a screen. It was something like this, or a very beautiful woman in the beach, so something like. And then this other quality expert who was with me was really looking at the screen and said, "The eyebrow is pixelating." So this is how not normal people think about video quality. Okay, so let's walk a bit the path that I have been walking in the last 20 years, and hopefully give you some ideas on where we are today and where is technology today, and especially why. So my first contact with video quality comes, so the guilty is this guy in the picture, who's, by the way, sitting here. Jesus, thanks for coming, really. So he was my, really my first project manager at Telefonica R&D at that time. And we were doing some tests with the first AVC encoders for digital television, for Imagenio, if you remember that name, like lots of years ago. Okay, we wanted to select an encoder. We have like 4 vendors. And then we wanted to prepare some tests for video quality. So we did what was in the standards by those days, so BT500, if you know it. So it's basically cutting a few 10 seconds cut of video. We selected 10 clips like these ones. We had 4 encoders. We selected a few different bit rates, and we had people seeing the video like in this protocol. So you see 10 seconds of video, and then you vote from 1 to 5. Then you see another 10 seconds of video. You vote from 1 to 5. So you can imagine like seeing the very same 6 clips at slightly different compression qualities for like half an hour. So very a fascinating test. And then you take the mean, and this is the famous mean opinion score that you all know about. And of course we did that, and results sucked. So we did everything like following the protocols, and then we would try to make some numbers. We were really not able to make any decision except seeing something obvious. So one of the encoders was really bad, and we detected it, but we didn't need a test for that. And we were not able to detect any other thing like that. So this is why I thought, okay, I could probably research a bit more in the topic. And by that time, I decided, while I was working, to start my PhD. And thanks Narciso, who had just arrived, because he was my PhD supervisor, and the other responsible person of me taking this journey. So we started, research. And if you have explored a bit on video quality, you might see like taxonomies like this one. So if you ever see a taxonomy like this one, beware. Because normally you have a lot of options, and none of these work at all. Okay? So beware of any paper or any presentation showing a taxonomy like this, because probably is not telling you the whole truth. In fact, I tested some of the state-of-the-art methods, and again, I didn't find anything that really worked. Then I looked a bit more into the state-of-the-art, and I found that there was a very big effort in the year 2000 by a large amount of people. It was called the Video Quality Experts Group. Now I'm a member of this group, but I wasn't a member of this group at that time. So they tried to standardize the best possible video quality metric that they could. So, and different companies and universities competed to find and they did proper tests following the standards and so on. And the conclusion was that none of the proposed metrics worked at all, and none of them was significantly better than our old friend PSNR. So basically, this was the state of the art when I started doing this research. Nothing, and this is the reason why most of you, or some of you, might still be using PSNR, because, again, it's not so easy to do something which is better than simply looking at the mean square error of your pixels, okay? The thing is that it had worked for speech. Okay, so this guy is Sebastian Müller. He's one of the top guys in video and audio quality in particular, and he did his PhD by those years in speech, and he wrote a book in the year 2000 about video quality or quality for speech communication, and summarizing all the conclusions and the research so far. And these kind of methods were originally designed for speech, for basically phone calls, and it worked really well. So by year 2000, they have this subjective protocol which really worked for speech. They have a full reference method, 2001, which was really, really good, and even a parametric method. So even a way to predict the speech quality just by measuring things in the network, and it worked quite well. So the thing is, for speech, things seem to be working, but for video, when they tried, I mean, they very, very, it happened with MPEG, so MPEG was working really well, so we can do the same with the quality, let's go for it, and we failed, let's say. So we had to, we as a research community had to start slowly again, and then we start by simpler steps. And this guy is Al Bobik, another one of the key people in video quality as well. And he's the creator of SSIM, and probably it's not his best work by far. He has lots of much better works, but it's definitely his most famous one. It's about 2004, and the thing is that it's perceptual in the sense that it somehow models the statistics of the image in a way that might have some relationship with perception. Okay, it gives you ideas in the paper, like for instance, this compared to this and this one. Well, we don't see so much the difference, but it works better than PSNR to some particular defects. In practice, it's not much better than PSNR. So if you have tried both methods for your daily work, it's not very much better. But it works. It's from 0 to 1, so it's kind of easier to interpret. It is not PSNR, so you can say it's perceptual. You can say it's more modern, let's say, and he put very simple and straightforward to use MATLAB code out there so that everybody could download the MATLAB code, run the test, and publish the results in the paper, which is probably everyone does these kind of things today, but 20 years ago it wasn't so frequent that people gave the software for free, and he was a very clever move because it gave him a lot of credit, and it gave him a lot of power to keep working and be in the forefront of the research. By the way, he developed other stuff like visual information fidelity, which works much better, and it's a key part of VMAF. I will talk about that later on. Okay, but so we have SSIM. There are other initiatives by those times. So this is Margaret Pinson. This is the chair of the Video Quality Experts Group. She is also the person who knows most about video quality in the whole world by an order of magnitude to the next one. So I'm a total newbie compared to Margaret. So every time I talk to Margaret, I come to an idea with her, and then she very politely, because she's extremely sweet and polite, tells me that this idea was tested and validated by somebody else 25 years ago. So she's and she worked slowly together with some colleagues in a video quality model. It's called VQM. This is the NTIS, which is the institution that she works for. It's part of the United States public agency. And he was able finally to have, so the final version of her model, which is the 2014, is probably today the best video quality model. So probably even up to some point better than BMAF. The problem is that even if it's also publicly available, it's not so handy to manage, interpret, and so on. So it's not so easy to integrate into your workflow. But still, it's there. But it wasn't ready for the market in the sense that it was not so easy to put it into your workflow. So this is why it's probably very known in the research community, but very not so well known in the industry. This VQM model. I'm running a lot, so but anyway. I have lots of slides, so I need to go quick. And then we have the other element of the video quality that's also relevant is, again, this whole idea that worked for speech, that if you measure some things in the network, you can somehow predict the quality, okay? Well, you can follow this path. somehow. So you know that if you measure the bitrate, if you measure packet losses, if you have like digital television, if you know the resolution, if you maybe characterize the video in a way or another, you can learn some parameters that let you predict the quality of the video. Again, this has been also a long research path from a lot of people. This is where a lot of people in the standards community has put a lot of effort on. This is ITUT has like I don't know, 10 different recommendations on diverse variations of these models. This is Alex Stracke, probably one of the key people pushing this initiative in the world. This is from Ilmenau University in Germany. And little by little now, we finally have some parametric models that work relatively well. So up to some point comparable to BMAF in some scale. So, but I mean, only in the context of adaptive streaming. In the context so we are still in the IPTV era, and models were not so good, and especially they were very complex. So you can see a bit the structure over there. And this is one of the simplest ones, so you need to take into consideration a lot of parameters and merge them in very complex and trained ways and so on. So somehow they're overtrained, and somehow they are difficult to extrapolate if you change a bit the conditions where you play with it. So this is kind of a bit of the research paths that we're taking to improve a bit the situation where we didn't know what to do. This is one of my things. The title of the talk. This guy is Jesus Gutierrez. He works in UPM. He's a researcher, and a close friend, because he helped me finish my PhD thesis. And we did this experiment together because other thing that we didn't like. The format is horrible, but anyway. Other thing that we didn't like about the experiments is the boring thing that I told you before, that you need to have a few sequences that repeat once and a lot of times. So basically, imagine the experiments that we use to calibrate all these quality methods are doing with this stupid method that I told you at the beginning. Like we have only 6 videos that we repeat them a lot of times with different compression rates, and we trust that these results really reflect the quality that people is experiencing, and then we really train our models to try to mimic this behavior. And we thought, okay, maybe it doesn't make any sense because people don't look at television like that. So we wanted to design an experiment which in a way was handled in a similar way. So you watch 6 seconds of video and then you score the quality. But you look at something which makes sense and something which could be interesting to you. And by that time, Spain had recently won the World Cup. So we decided that the best sequence that we could thought about was basically the moment when Iniesta scored the goal. So at least, we could figure out that people were going to take some interest in seeing it, because even if they knew what's going to happen, but we also have the speaker, the motion and the moment and so on. So we did the test with that, and we got some interesting results, and in practice we were able to measure the things in a way which was, from our perspective, much closer to what people was actually doing to see the television. And it was not only us, I mean other researchers I will talk about later on a bit were also following this path. So these were like the small steps that were being done before the arrival of the adaptive streaming. I will talk a little bit more about a couple of details. This is Greg Cermak and Marcus Fiedler, two key people with great ideas in video quality. So if you think about this moment in time where video was basically digital broadcast television, so like you have HD video or 4K video or whatever, but it's a single resolution, then basically the main factor to determine the quality of your video is the bitrate. And in practice, if you know something about the video, and if you measure the bitrate, you normally can say a lot about what the quality is going to be. And interestingly enough, it's going to have this shape where the first megabit per second really help you in increasing the quality, and then it saturates a lot. Then this was kind of well structured by Greg Cermak, and Marcus Fiedler did a very famous paper in the research community, basically posing that this kind of relationship had to be exponential, so that this was like exponentially like growing to the saturation point, basically. So this is a bit of the basics of video quality, and this is what we took us a lot of years to learn. When somebody discovered that the best thing of delivering video to people at home was simply compress it at a lot of bit rates, split it into files of 1 megabyte size more or less, leave all the files into a server, and let the client handle by itself. And this, as you know, this simple and stupid idea has changed how everything is done in the industry. And it also changed how we could attack the quality problem, basically because now we had a much larger range of qualities in the same service, which is very good because we don't really need to go into the detail of the dB of PSNR or the 0.1 factor in BMAF or whatever, or 0.1 factor in MOS, because now we have a large range of qualities, okay? An interesting part from the compression perspective, and you come from the industry, so you know better than me, is that in practice what you really do, even if you want to see the video in HD or 4K, is that you compress it at different resolutions, because you have these curves at each resolution, and basically to have the best possible quality, it is better to use low resolutions for low bit rates and high resolutions for high bit rates, which is a very practical thing, but it has also some interesting implications in terms of quality, because somehow we can see that this is like low resolution, so this is like SD quality, this is like HD quality, and this is like 4K quality. So again, we are starting to think again in quality in terms of the resolution. I will formalize it a bit at the end of the talk. And this, in this context, is where Netflix people come. This is silly. This is a very nice man, a bit shy, and the father of BMAF, with other people, but basically most of the work is his. So BMAF is something simple. It really started because they needed a metric to tune things much better than asking 3 experts. Basically, this is not from me. This was from this sentence is from Ann Aaron, who is the responsible, the boss of these guys in Netflix. And it's simply a combination using a support vector machine of 3 metrics. So one is this visual information fidelity from the SSIM guy, from Bobik, the tail loss metric, and temporal difference. So basically, I tried to remove the thing. Okay. But it works. It works similar to VQM, but it has 2 key advantages. It's something which is, well, first of all, it's something which really works better than PSNR and SSIM. So it's a metric which really works to predict video quality. It's open source and plug and play, so you can introduce it into your pipelines in a very easy way. It takes a lot of time to compute, but that's a different problem. And it's backed by Netflix, so you can use it and you can say, okay, Netflix uses it. Okay, so that's great because this metric, as SSIM in the past, by the way, never really passed like a global evaluation from independent labs and so on. It was simply adopted immediately by the industry and by the research community because we needed something like that. Okay, the thing is that it works, and it works really, really well. So we try to, and this is Marta, by the way, thanks for coming. Something that Netflix did when developing the metric was, okay, what happens if I watch the video in a mobile phone instead of on a TV screen? And then they developed this phone model, which is basically a fine-tuned version of the global model, and it works really nice well for phones. So when in our research, we were starting to work with 360 video at that time, some years ago. It was Marta's PhD thesis. I was lucky enough to be her supervisor. And we thought, okay, maybe we could also tune BMAF to measure the compression rate of video in 360 video. And we found that we could use BMAF without any tuning. And it worked really nice for 360 video. The thing is that another PhD student in the UK, it's Navajit Barman, did the same for gaming content, and it worked perfectly. And another one from Ghent University, that's Sam van Dam, worked it for point cloud video, which is something very strange and research like today, and it worked perfectly as well. So for BMAF, surprisingly, even if it was not previously validated, it's really a metric which is really reflecting what people is scoring in these ACR tests. Okay. And so the thing is, okay, and now what we have to do probably is improve a bit these ACR tests, as I said before, because we are still using in the industry this idea of repeating the same test one and again. The Iniesta goal wasn't so successful as methodology in general. Okay. So now we have a slightly different aspect of how people score, and I will not go too much into the details, but basically Lucian Janowski, together with Margaret, don't forget her, developed this fancy model saying that basically you could model the quality rating of a single user using a random variable, basically a Gaussian random variable. So this is interesting because it says, okay, a user will rate the true quality, so the most, plus his or her bias, which is something systematic, but some Gaussian noise depending with some variance, which depends on how inconsistent the user is and how difficult the sequence is to rate. And they proved that the model is reasonably true, and it's actually used in BMAF to train the model and tune how things are done. And this is where I joined the video quality expert group and say, okay, Lucian, I like your model. He didn't know me, by the way. I just approached to him in the meeting and say, I like your model a lot, but have you thought about what it means? It means that, okay, if your model is true, you can have one single user repeating the same measure again and again and again and again, and you will reach the most plus his bias. So if you can estimate the bias, you can get most with one single user. So he looked at me like, I like your idea, let's torture people. So we decided to try if this idea was true. So we found 26 people who were friends of us before the experiment, who volunteered to do the same subjective test 10 different times in 10 different days, so that we could see if it was really true that they were able to approach to the same quality after 10 repetitions. The answer was no, but they were approaching for the very first 4 or 5 times. So basically, if you do the experiment the first 4 or 5 times, you really act as 4 or 5 different people, which means that you can cut the number of people that you have in your experiment by 4 if you convince them to do the experiment 4 times. But this is okay because you can with a number of 4 people doing the test 4 times, you could get results comparable to a 15 people experiment, which is good enough to get insights of how things are going. By the way, we finally put it into the standard. This was last year, so it's also an official method that you can use, and you can claim that you are using this few users with repetition. So this 4 protocol, which is recommended by International Telecommunication Unit. It's okay. It's fancy because we've used it also in some tests. If you need to calibrate a bit your coding, and you don't want to recruit 20 people, which sometimes is difficult, you could do the thing in the lab. During a week, they can even be experts. I mean, we had experts in the tests, we have non-experts in the test, and we didn't find any difference, which is a bit surprising. But the thing is that it is kind of surprising that this kind of tests worked similarly well with experts or without experts. Okay, in fact, when together with Marta, we repeated a similar experiment as the Iniesta's goal, with long videos and so on, with 360 video in this case. And we discovered that, again, it was the same if we got the rating in this valid way that we rate while the conversation is happening and you know about everything that's happening, or if you simply random all the clips and we did the experiment in the old way. So this old way of doing the experiments, which doesn't make any sense at all, seems to be robust enough that it's impossible to break. So basically, if you try to design an experiment that you put people in a condition who is like should be closer better mimicking how they look the video at home, and you repeat the test, you will get basically the same exact results than if you do the formal protocol of this 6 sequences coded at a lot of different bit rates and the boring stuff. In fact, we have Camille in the audience as well. He looked younger in the picture than today. But he has devoted his whole PhD thesis in trying to break ACR, and he has discovered that it doesn't break ever. Okay, so this is extremely robust. We don't exactly know why. We have some insights. He's a psychologist, so ask the insights to him, not to me. But yeah, the thing is that this ACR works. So I don't know if you are. I hope you are not too lost so far. So I'm going to the final sprint with the purpose that you finally get lost, okay? I'm telling you about my last year paper that I love. So you need to somehow bear with it, okay? So we are in the situation where we have the metrics, we have the tests, and we have BMAF, so we are more or less happy. And now we have parametric models that work. We are more or less happy. I was not happy because parametric models work with an equation like this. Okay, you don't need to care too much about that. But they estimate most, but they first compute something that they call the transmission rating, and they put a magic equation and say, okay, if we can map most from transmission rating using this stupid equation, and then we have a shape like this. And it's been there in the standards since the age of the speech test, like from 2000s and so on, and nobody knows why. So I tried to figure out why, and I discovered the reason. And then I found a paper from the time where research was done in the proper way, so from the 60s, doing by this guy who unfortunately passed away last year. I don't know him. He's called John Kavanagh from AT&T. And it was the best test ever. So they inserted noise into the phone calls of the people of their department, and then at the end of the call, they called the people back to rate the call, and they ran the test for some months. So, and they didn't know exactly what to do with the numbers because nobody was doing. I mean, there was no theory, there was no practice for that. They invented basically this 1 to 5 scale in this test, by the way. And they found something very interesting is that they repeated the test in 2 different times and they have different results. Okay, so they did the same test in 2 years in 2 labs and results were different. They were very correlated, but they were different. And the way they found the way they found that they could mix those results was assuming that the distribution that they have was a normal distribution, basically. So people rating different scores in a continuous way, let's say. And then, all the people here would rate 1. So from minus infinity to 1.5 would rate 1. These guys would rate 2. These guys would rate 3, 4, 5. So they try to map the histogram of scores to a Gaussian shape, find the mu and sigma, and then, since they have mu's in 2 different scales, they needed to decide, okay, we need a reference scale. And they used the scale that they already have, which was this transmission rating scale, which is basically the dBs of attenuation in the phone line. This was a scale that was invented in 1930. So they have been using this scale for 50 years. So this was a scale that their bosses knew. So they used that. And then sometime later, somebody found that this could be a good approximation to translate from this mu to the actual MOS. Okay. These ideas, so this shows like a statistical behavior of the scores, let's say. And these kind of statistics have been also analyzed in a separate way from the research community. This is Tobias Hosfeld, probably the person who has analyzed more about this kind of score distribution in video. And this kind of, he had already found that modeling the distribution, the scores as a Gaussian distribution was the best actual way to measure the scores in video quality. And if you remember, it looks like the result of this normal model that Lucian and Margaret proposed 3 slides before. Okay. So the thing is that if you process the video scores in that way, and then you take a test which is done in a mobile phone and compare the same test done in a TV screen, then the results between those tests can be mapped linearly, which has some implications that I don't really want you to get so much, because you need to think a bit about that. But basically it means that if you process MOS this way, you can have, so meaning this point has, or maybe this point has a quality which is 5 in well, whatever. I think they're wrong, but this, you can have a point which is with a quality which is 5 in a mobile and only probably 4 in a tablet, because a tablet is bigger. Okay, so you could say that the MOS of this point is 5 or the MOS of this point is 4, but you could also say, okay, it's the exact same point because it's the exact same video. So you can simply say that the MOS is a number and then I map it linearly. And you can put any number which goes linearly with this scale, and there are two candidates, and this is still a hypothesis, but there are two candidates to map this linear weight, so to give units to this linear transformation, which is bit rate or much more probably pixels resolution. So basically, this is a formal way. So there is a formal way to translate MOS at different resolutions to a reference resolution value, which means that we could do in video the same that people in speech has been doing, even if they don't know too much, have been doing for the last 50 years, which is talking about video quality, not in terms of MOS or whatever, but really in a very precise and formal way, talk about video quality as this is HD quality, or this is SD quality, or this is 4K quality. So basically, and I hope I haven't been so boring today, this is how you should think about video quality. So I expect to convince you that you can start here, like, okay, this is HD, and you can make a lot of research and numbers and so on, and very seriously decide, okay, this is mean opinion score of 3.4, but really the right way of thinking about quality is the formalized resolution hypothesis. And that's all I had to say today. Thank you very much for listening.